this video, we will be learning how to use tables to determine remainder patterns. And as we get into the problem, you'll understand what I mean. And also, I would like to talk about the three main properties of remainders. So here's the first one, and I covered this in a previous remainder problem playlist as well. So if you want to go check that out, you could do that as well. So the first one is that the sum of remainders is equal to the remainders of sum. Here's what I mean. 17 divided by 4 is equal to 4 with a remainder of 1. And we also know that 39 divided by 4 is equal to 9 with a remainder of 3. So if we add 17 and 39 together, the dividends together, then we get 56. And what's 56 divided by 4? Well, that's equal to 14 with a remainder of 0. And as you can see, because 1 and 3 added together is 4, that can make exactly another group of 4, so that's why the remainder was 0. But say even if this was 38, 38 divided by 4 would have a remainder of 2. Now let's add these two together. We get 55. 55 divided by 4, and we have a remainder of 3, right? Because the closest multiple of 4 to 55 is 52. And see how after we added 1738 together to get the bigger dividend, which is 55, the remainders added together as well. 1 plus 2 is equal to 3. Well, it's not just sums that work with this. The second property that I'd like you to know is that the difference of remainders is equal to the remainder of difference. For example, if we have, again, 38 divided by, say, let's do 5 this time, is equal to 7 with a remainder of 3. And 49 divided by 5 is equal to 9 with a remainder of 4. And now if we were to subtract 38 from 49, we'll get 11. And 11 divided by 5 is equal to 2 with a remainder of 1. Why do we get a remainder of 1? Well, because 11 is the difference between 38 and 49. And 1 is the difference between 4 and 3. So still, if you take this difference of the dividends and create a new division equation with it, then the remainders will subtract as well. And my final one, and you probably guess what it is multiplication, which is that the product of remainders is equal to the remainder of product. And I'm not going to explain that because I think you get the idea. Well, today we will be using those three concepts to help us solve this problem. The problem is fairly simple. It's just one sentence. What is the remainder after dividing 2009 to raise to the 2009th power divided by 9? What is the remainder? So in math problems, when you see really big numbers like 2009 and especially exponents, you need to think smart, which means there's definitely going to be a pattern, right? It's not exactly asking you to multiply 2009 times. So the useful tool with patterns is to make a table. I love making tables. They're just so straightforward and it's easy to get the pattern from them. So over here, I'm going to write, so this is the top row is going to have all the different dividends. And the bottom part is going to be the remainders it has after being divided by 9. So our first one up here is 2009 itself. So 2009 itself, well, 2009 itself, it's just a 4-digit number. So you could just divide it and you will get a remainder of 2. So the remainder is 2. And our next one is going to be 2009 raised to the second power. Now you might be thinking, well, didn't you just say we have to think smart about this? Why are we putting exponents as the dividend? Well, first, how else are we going to get the question, get the pattern? And the other one is, we already know that 2009 divided by 9 has a remainder of 2. So let's use the properties we just learned. 2009 divided by 9 has a remainder of 2. So if 2009 squared, it's really just 2009 times 2009. So that divided by 9 is going to be the remainder times itself, right? Which is 2 times 2, which is 4. It's going to have a remainder of 4. This is the property that we learned. The product of remainders is equal to the remainder of product. Now our next one is 2009 cubed. This is 3 2009s being multiplied together. 2009 times 2009 times 2009. So, or you could think of it as 2009 squared times 2009 raised to the first power. So you could do 2 times 4, which were the previous remainders, and you'll get 8. We do this again. 2009 raised to the fourth power, and you do 2 times 8, which is 16, except you can't write 16 there because 16 is already greater than the divisor, which is 9. So 16 and 16, we can fit 1 9 into it. So if we take that 9 out, we have 7. So this would be 7. 2009 raised to the fifth power, and we get, same pattern. If we get 5, and 2009 raised to the sixth power, we get 1. And now we know that we have reached the end of the pattern, because at 1, everything just repeats again. So now we have the pattern, and it's a rotation of 6. So it's 2, 4, 8, 7, 5, 1. That's 6 terms, and then it repeats again. So if there's 6 different numbers in one rotation, let's divide. And as you can see, the first one, 2009, has a exponent of 1 and 2 and the 3 and the 4. So if this 2009 has a exponent of 2009, then we can divide 2009 by the number of things in each rotation, which is, again, 6. There are 6 numbers in every rotation. In 2009 divided by 6 is equal to 334 with a remainder of 5. So the answer would be the remainder on the 5th term of every rotation. So let's go to the beginning of each rotation and count. So this is 1, 2, 3, 4, 5. So our final answer is 5. Now I just want to be clear again why we got 5 as our answer. Is our 5 coming from, is our final answer 5 coming from here or here? If you answered here, then you're incorrect, because this is just telling us the which term in every rotation there is. This is from 2 to 1 is a whole rotation. So the 5th one in that rotation, we count 1, 2, 3, 4, 5, okay? If this was another number like 3, then the final answer would be 3. If it was 9, then this answer would be 9. But again, our final answer is 5. So thank you for watching with your Inquisitive Kids, and see you in problem 4.